Another draft physics video production such. So we do have an animation of sorts. It's getting there. It's close, but it's not enough density of little bits compared to the movement of the electrons and protons, so they're not really doing what they should do yet. And so still needs work. And it is kind of rough on the computer, so I'll close it until I have it better working. I have to learn how to read the code. Yeah. And anyway, but it's interesting. It's doing something. It's just not exactly doing what it should do. There's no reflections between the red ones. There's just not a high enough density of little things compared to the big things, and so I have to slow it down. I think slow down the big things so more stuff can hit them in before they move out of their positions. I mean, generally speaking, it's doing something similar. The red ones aren't close to each other very often, and the blue one does tend to hang around one of the red ones, so it's doing a little of what it should do, but not nearly enough. So, on to other things and such. Aquarium webcams and such. Just looking for still images, that update every few minutes. So, for stuff I'm working on. Anyway, so comments should take a while. Alright, so I guess we'll do holiday first. Which is sort of an interesting subject, mostly. Hopefully the computer looks a little bit. Anyway, I'll try to explain better. I have two fridge magnets. Well, they're probably a bad example because fridge magnets are really complex magnets. I can feel the force pushing, repelling each other. You mean the solid type of magnets, okay. I use my muscles to overcome this resistance and touch the magnets together, and as they touch, the force becomes impossibly large. So he's just talking about the fact that two things, they don't have to be magnets. You push them together and they, you can't push them into each other. And magnets give you the little extra bonus of, if you have them same poles, they'll give you this, there's something in the way, but you can push them together, generally speaking, unless it's a really, really, really big magnet. Alright, I'm unable to push them such that they merge into one. Yes, yes. Let's see. At that moment of touching, the nature of the force pushback, I feel completely changes, increasing 1,000,000-fold. Yes, once the magnetic force that you're getting is a tiny force, so to speak, compared to the inability of atoms to penetrate each other. I don't recall you explaining this transition from plain old repulsion, inverse square law, to practically immovable. Right, so there's two concepts there. There's what the atoms produce as a force to other atoms, and then the fact that the atom isn't going to let some other atom go through it. And so it might be E equals mc squared kind of stuff, but let's see. It has to do with the nature of the atoms, and not so much with the nature of what they excrete. I guess I would say it that way, because what they excrete is completely dependent on the proximity. So I guess we'll start with, okay, so I'm just going to do the protons and neutrons as a net positive, so that's in the middle, and then the idea is that you have these electrons positioned. I'm going to use 4 just to illustrate. I mean, you can do it with fewer, but it gets more complicated in terms of what kind of drawing you have to make. So the idea is that there's repulsion between the electrons, and we'll draw attraction. Hey, maybe we can use 3 colors. I don't know. Boldly attempt something different. And then there's attraction, okay, between the proton and the electrons, and that no electron can move closer to the proton without offending, that is, moving closer to the electrons. It can't do that. So I probably should have done this force in red just to illustrate the point that this is a repulsive force. Alright, now I've speculated that this configuration is created in high pressure. So it's not created in some sort of relaxed condition. It's created inside of a sun or inside of something in which the pressure is very high. So this is a very high pressure arrangement, meaning there's a lot of stuff here. You know, this is really quite intense, and this pull is quite intense, and so the whole thing is made out of a very there's a lot of little bits keeping this together. Let's see if there's a better way to say that. I mean, obviously this wouldn't be a lot of bits here. Okay, so that's the low pressure, but the bits inside of here would be a lot of bits, say, holding the electrons and protons together. Well, at any rate, the point is this is, I guess, the real energy of that's keeping the whole thing together. So the idea is when these electrons are a little further away from the proton, the center, this pressure is a little relaxed, okay, but it's less, you know, there's less pressure between the electrons, and you know, I'm just trying to get it straight in my own head whether close. The point is that the polarization of this atom is dictated by this distance between these electrons and this proton. And if the distance increases, you could say, okay, it's more negative from this perspective and more positive. I'm not going to bother polarizing the atom. So it would be more positive when it's in this, from here to here, that's positive. And then when it's moved to here, then it looks more negative from at least this, well, you can't see that perspective, but from down here, okay, looking at it. So the further away the electron gets, the more negative the atom gets, let's say. It might be the inverse, but let's just say it gets more negative, and it gets more positive the closer the electrons are to the proton. So the point would be, as it's radiating that profile, let's call it, in terms of that's the magnetic field. So the magnetic field is coming off the view that somebody gets from a given perspective. So if it's magnetic, if it's positive at 1 minute, then okay, you'd say this is the north side of the magnet, or the south side. Let's just make it the south, for that's probably the more correct way to say it. So when it's close in, then it's a south magnet, and then when it's far away, it's a north magnet in terms of what it's radiating to the world. So that's the magnet part you feel, all right, because the atom can be polarized. And by being polarized, then probably the truth is that one side gets closer to the nucleus and one side is further away. So that's probably the more realistic way to look at it. So a piece of iron has an atom that can do this polarizing thing, where one end is further from the proton than the other end of the configuration of electrons. So from one side it looks decidedly positive in terms of its net field, and from the other side it looks decidedly negative. Okay, that should have been okay. So that's the energy it's producing. So the effect it has on the rest of the world. Now the problem is if what you're trying to do is say, okay, what if I smash another piece of atom in? So the point would be is the electrons are conveying the pressure. So everything, like you could argue, is sort of electric in the sense that you have these different. Oh, I got red in my blue. That's pretty. I mean, blue in my red. That's dangerous. Anyway, so you have atoms next to each other, and as I sort of pointed out, let's say they're sharing that electron. So this electron, they're sharing it. The idea is that the pressure, say if you pressurize this is you push this electron closer, you're pushing these further away, in essence. And of course this one is ultimately going to get pushed, and if it pushes, it's going to push on these other electrons. And so any incursion by an electron here, you're pushing with your new atom. You have some new atom here, okay, well, whatever. So this is, I should have some way of drawing an atom. So that's an atom. Yes, well, just pretend this is an atom, this is an atom, this is an atom. So you're coming in, you're encroaching with your new atom. So first you're going to feel the force effect. That is, you're going to feel there's an electron in this atom over here, and then you're coming in with your new atom. First you're going to feel this repulsion. That's the effect you feel. And then you're going to, as you push harder, you're going to be now pushing these electrons, and you're also going to be pushing into these other atoms. And the point is now you're going to have to move all of their masses. So now you're going to try to start moving them. You're not just sending pressure through the electrons. You're actually starting to move the atoms. And to move the atoms, that means you're going to move this one, you're going to move this one, you're going to move this one, you're going to move this one. So the more atoms it has, the more mass you have to move. That means you have to put in an awful lot of pressure, because it's going to equalize into all these other atoms. So anything you push in, is going to go through all of these atoms, and they're essentially going to push back, in the sense that you're going to have the equalizing effect is going to mean that when you put pressure in, that you're starting to pressurize these electrons. You're pushing them closer together, and so they're going to create more pressure because you're getting pushed closer together, which means they're going to get more pressure. They're going to have more force pushing back. And so any force you push in to move the atom is obviously going to be met with a ton of force back. You're going to get a lot of equal but opposite reaction until you actually put in enough pressure to move all of that mass. So the more mass you are trying to push, the harder it's going to be to push. Now if I push something that's on a slippery surface, it just kind of pushes kind of easy. But if I hold it in my other hand and then I try to push it, it's not going to move so easy, right? I mean, it's really easy to push this thing, if I'm not putting any pressure on it. But if I put pressure on it, it doesn't push so easy, because now I'm pushing against pressure, and the atoms aren't going to compress. I mean, they're not going to compress any more than they're compressed. You just can't compress these forces. So the fundamental argument is that there's a point where electrons can't be made to go closer together, because this, well, I have to draw it higher, sorry. The idea is that there's the ping pong paddle thing. There's a force between the electrons bouncing back and forth, and so the closer I bring them, this force gets faster and faster. The number of impacts increases, and there's sort of like this idea it could go to some kind of infinity. So you can't really bring these electrons too close to each other without the pressure increasing proportional to how close you're bringing them. So the closer they get, the pressure goes higher and higher and higher and higher. So there's just no way that they're going to do that. And again, the atoms themselves have already been in high pressure, so they're already in a high pressure state. So they're not very yielding. They're not going to squish together really easy, because they're already 10 million foot-pounds of pressure between them, so to speak, or something. So to push one means to push all of them, and that's why you're met with a tremendous amount of resistance because the electrons are already pressurized, and so you're pushing against something that's hardened by 10 million pounds of pressure. They're already so close together. Yeah, that kind of thing. So you can only push into something that has low pressure. You can't push into something that has high pressure. So if the atoms are not rigidly bound in like a metal, where they're stuck to each other and they're just kind of freely bouncing around, well, then you can push into it. You have some kind of latitude. The atoms will get closer to each other. But the atoms of some kind of elemental substance, hard stuff, like pieces of plastic even, those atoms are they've already taken all the extra space out. They're as close as they really want to be. And any closer you make them, you're really making electrons closer to electrons, and they're already bound by a lot of pressure. So you really can't push one without pushing them all, which means whatever their mass is what you're really fighting against, and their mass is determined by what they're connected to. So you're not pushing against this piece of plastic, you're pushing against my arm and everything I'm connected to. I guess that'll have to do. But they're really two different subjects. I mean, the rigidity of the inside of an atom is kind of a different subject than what is the atom excreting. What comes in and what comes out is one subject. What's going on inside the atom is another subject. I mean, pretty much. Alright, some kind of Tesla bullshit here. Let's do this quickly. You make some interesting counter arguments to his video, but you are every bit as non-credible as Jimmy is. Well, that's for the history to say, or for somebody's judgment. I'm saying his arguments are completely incredible in that they're just urban legend crap. He read it somewhere and that's it. I've read Tesla, okay? I've gone out and looked for everything Tesla wrote to see what Tesla actually said. And that's a difference, right? I'm reading a newspaper article versus what he read, okay? Tesla wrote for, I think, whatever the Farmer's Almanac, whatever the hell it was, whatever the popular magazine of the time. He wrote a little five-part series, and it has his life history in it and all that kind of wacky crap. But anyway, so it's sort of a biography, but a very shallow one. But anyway, I've read all that crap. So, I mean, everybody can make assertions, that's right, but everybody's not going to sit there and give you a bunch of footnotes to all their sources. That's just kind of silly. Okay, so either, so that's the extent of the argument. I'm making the accusation that Jimmy's analysis is based on superficial investigation. That's my argument. You can buy it or not buy it. That's your choice. Why would you post a video like this without proof that your argument is correct? And what do you want is the form of proof. I kind of prefaced the argument with, I've looked up a lot of Tesla stuff. Read some of his patent papers. He writes a lot of stuff in those patent papers, and through those sources, investigated, and the whole thing with Edison and the rest of it. What can somebody say? Neither you or Jimmy have posted any sources for your information. Well, I don't know if there was no sources. I think I did point out the things I just pointed out here. So you are part of the problem, sir. No. I'm countering what other people are saying, okay? They're saying something. They're making the assertion that something's true. And I'm doing what you're doing. I'm saying, well, why do you say that's true? Because I don't see it as true when I go looking. I don't have the obligation to undo their lies, okay, with anything other than the assertion that they're lying, that it's bullshit, that it's crap. Okay, I wasn't the one who started it, so to speak. Okay, I don't have any interest in Tesla except to knock down this incessant propagandizing that Tesla invented everything when he didn't. Okay, it's just a fact. He didn't invent all these things people think he invented. He didn't invent AC current. He didn't invent all this crap. He modified a motor. I mean, I would say that he invented the three-phased um, motor. Yes. Okay, but he didn't invent everything else. So whatever, fuck you. This guy does write a lot. Okay, so Jason. Alright, so he's the guy who can't figure, so he can't see the density. So he says there's a density problem with energy in the universe. And I've argued that the easiest way to understand where the force could come from is to understand the cosmic microwave background radiation. It gives you an illustration of a source of energy coming from everywhere in space, apparently, looking as if. So we look up in the, so here we are on Earth, we look into the sky, and basically the idea is that we see all this radiation coming from everywhere in the universe. So no matter where we look, we see a bunch of photons, okay, electromagnetic radiation in this ray form, okay, in hunks that we can detect. And as I've explained before, the catch is, so that's a source. It looks like it's coming from everywhere. It doesn't look like it's coming just from suns and just, it's coming from the black space. It's coming from everywhere. Just this constant source of radiation from the outside, all around the Earth, from every perspective, coming in right for us. And as I've argued, these photons, these rays of energy, okay, we can only detect it if it's a certain size. So just like light, and the fact that we can only see photons when they hit our eye with sufficient a number of these things, okay, and the number is approximated to be about 6. So we need 6 things at a frequency. We need 6 quanta of frequency, of separation between the thing, the event, 6 wavelengths, 6 lumps. And if we don't get those 6, it still could be energy. Okay, 4 of them could be flying into your eye right now, and you don't see it. Okay, so there's 4, nothing. There's nothing. You don't see it. It's like it doesn't exist. It's invisible to you. It's invisible to your detecting devices. It's indivisible. You can't see it. Now, we can make instruments that can detect maybe 3 of these things, but it still can't detect 2. Okay, so there's still a limitation. Let's just say 4, just to, So we can make a machine that can do 4. So it's a little better than our eye. Okay, and the trick is, though, if we try to make it more sensitive than that, right, doing 4, all of a sudden it sees photons everywhere. Everywhere you point, it's seeing photons. So that's sort of a giveaway that, there's a whole bunch of this stuff. So the cosmic background radiation we're seeing, so let me just illustrate, you can have 1, you can have 2, you can have 3, at, whatever, 500 hertz or something. It doesn't matter, 500 nanometers, light. You can have 4, right? And the point is we only see this. And let's say we can only see this one down here, right? We can only see pretty big hunks with our eyes. We can make instruments that can see this. So we can see this part of the cosmic background radiation. The argument is, is the cosmic background. The argument is the cosmic background radiation has a ton of rays this long, and a ton of rays this long, and a ton this way. And it's not only a ton, it's exactly disproportional. That is, the line goes this way, all right? So the amount of stuff in this form is gigantic. The number of rays, so just think if you had to make these things, right? If you had to flip coins and get 1 head, well, that's easy. To get 2 heads in a row, well, that's a little harder. And to get 3 heads in a row, okay, that's even harder. And 4, even harder. So the stuff we see is the rare number of the photons. The rare photon is the one we can see. And, and we can detect some that are, we can do a little better with our detectors. But there's the huge part, the big part, the part where there's a ton of them, where everything 3 heads and less. So every time you get 3 heads in a row, Okay, you count that. But every other flip that isn't part of 3 heads in a row or 4 or 5, you don't count. And I'm just saying that's the biggest volume. That's the stuff that happens most often. So the cosmic background radiation is thicker. It's insanely thick. And we only see a little tiny bit of it, the energy that's out there. And that's why gravity's invisible. That's why magnetism is invisible. Because it's made out of these little rays. It's not made out of these big rays. Alright. That's just to be clear what's being argued, so any of his misparaphrases about what I'm saying is clear. I'm saying there's sources that can be understood. That's an easy to understand source. We can understand that we can't detect certain radiation. If we jam a radio signal, for example, we can't receive it, can't detect its existence. So we're really dependent on our technology, and our technology isn't really that good at seeing all the energy. It only sees a tiny percentage of it. All right. At 1340 in the video on the 29th of October, you use light rays. I guess he's talking about the video he's making a comment on. You use light rays of distant stars to illustrate convergence in a spot. Yes, I'm just saying you can do it from any place. I'm just saying it's the point is that it's obvious that we're a small piece of the universe. Even the Earth, it's a small, tiny thing, okay, in a field of stuff all over the place. And obviously, it's going to appear from any point in space. A little thing is going to see the big expanse, the big giant circle of the bigger sphere that it's existing in. We're a little tiny dot in a giant sphere. Well, and I clearly pointed out the argument, so I shouldn't have to do it again. I clearly pointed out that, okay, you don't believe that if I made a hollow Earth, that inside the hollow Earth there would be, the idea would be, you couldn't sense any gravity. There wouldn't be any gravitational pull in any direction. You don't understand that concept, apparently, because that illustrates the point. But anyway, see where he goes. Of course this happens. Okay, so then why are you arguing with me? But I'm not sure it's enough to account for the apparent density of the force bits. Well, I didn't say the force bits are coming from stars. I'm just saying you can get an idea of it from that fact, that there's lots of energy coming from the universe. The universe is hitting us with energy. Yes, they converge, but for every such line that converges in a spot, there should be a lot of parallel ones. What does that mean? Heading for each neighboring spot. Yes, there are. Each place in the universe is going to get hit with a different image of the universe. If I move around this room, I'll see different photons reflecting off the objects. They're going there right now, even though I'm not sitting over there looking over here and looking at the photons that are going over there. They're going over there. Just like when I'm over there, I won't see the photons I'm looking at now. Wouldn't you need infinitely many sources, points of origin for the straight lines? No. That's the answer. Yeah, that's what I'll say to account for them. No. I don't understand this what you're complicating. Every object is shooting photons in every fucking direction. All right? I mean, that's the way it's basically working. I mean, there's energy in the universe. It's bouncing around, going all kinds of places, and at any one time on any one surface it can bounce this way, or there can be something coming in this way that bounces straight back, or it can go in this way. But the point is, anything radiating light is radiating it. Well, one photon goes that way, and one goes that way, and one bit of energy goes that way, and it goes that way, and it's all randomized. So yes, it comes out in straight lines in all kinds of directions. Yeah, I don't know what else to do for you here. account for empty space has possible points of origin would solve the problem. Empty. No, I'm sorry. There's no problem. You keep saying there's a fucking problem. There's no fucking problem. This is so fucking stupid. You say you agree, and then you really don't agree. Okay? The point is you can't. It's a fuck. I said it already, but I'll say it. I mean, why are you being such an obstinate asshole? The universe is a fucking box, asshole. There's little fucking BBs in it, asshole. The point is that they're random in their motion. They're always moving. They're bouncing all over the fucking goddamn place in the fucking goddamn box. There is no place here where, oh, there's no photons. There's no BBs hits here. No BBs hit here. No BBs hit here. No, the fucking goddamn physics is that there's the same number's going to hit you here. The same number's going to hit you here. The same number's going to hit you here. You can't escape it, you jackass. Fuck. Alright, anyway. It's a solution that is consistent with the infinite... Oh, fuck you. There's no solution problem. There's no fucking problem. Okay, maybe challenging you to account for the existence of parallel force bits. Fuck you. Or for each force bit would have been smarter way to go about it from the start. Yeah, fuck you. There's no fucking problem, so why do I need a solution? Oh, that's right, I don't. Though actually, now that I think about it, oh, you're not even thinking about this shit before you type it? Good, thank you for wasting my time. Some more. Your theory creates parallel lines of force bits sort of for free. There's parallel ones, there's unparalleled ones. The admission from a point means that this thing, say this object is this big, okay? There are photons that can leave this way, okay? Completely parallel. Hey, we turned out to all be parallel. And then there can be photons that are all parallel in this direction. There can be photons going this way, and there can be photons going that way, and there can be photons going that way. Every single path is a legitimate path, and the amount that each thing produces is immense in terms of the number of photons. Like the sun is producing an insane number of photons. So from one point in space, the sun looks big, right? But the sun isn't technically big compared to the universe. Okay. And it's actually creating rays that are going in all directions. All right. But it's also creating rays from that sun that are all in one direction. Or in this direction. All parallel. So it's creating parallel rays. It's creating these kind of rays. They're all coming out at the same time. Tons and tons and tons of photons in all directions. In all kinds of alignments. Diverging, not diverging, all kinds of arrangements. Alright, anyway. Look, the only reason why our eyes work is because of the pupil. The pupil cuts out all the other images. It takes away the problem. So if you didn't have a pupil, you wouldn't see anything. If you just stick a retina in space, the retina can't get an image because there's too many images hitting it. Alright. All you need... that's how they make holograms. I mean, I don't want to get into all this shit, but, you know. All you need is stars shooting light rays. Every now and then, they'd be hitting a proton. And my argument would be that would be rather insignificant because the light rays, the photons we see, are electron force at a frequency, not proton force. But anyway, that creates a lot of parallel lines heading for all kinds of points in space. Whatever. What do you know? Fuck you. Your theory already seems to solve this problem, so then why are you bothering me? Sort of looks like it might anyway. Still, I find it weird how it takes me of all people to address this. Why aren't more people at least trying? Addressing what? Again, what you're talking about, I can't understand it as a dilemma of any kind. Sorry, I haven't raised better objections or formulated better questions yet. Well, no, you just persistently keep saying there's some problem that needs solving that I can't find. It's an attempt of filling the void, as I don't see nearly enough people challenging or being interested in your theory. And so it helps for you to create more noise on the channel. That is me having to answer questions that nobody else asks because nobody else can see the problem either. Unfortunately, I may not be entirely fit for the task. Yes, it appears to be. Nevertheless, it seems worthwhile for me to challenge your impressive model of physics or to challenge my understanding of it. I don't understand the whole challenging thing anyway, but okay, if that's what people want to do, fine. I'm saying if you see a legitimate problem, fine. Okay, you're saying, because the way you're looking at it, there's some way that the amount of energy in places gets ruined by the tiny amount of matter that's in the universe, and there's just not enough mass in the universe. The distance between objects is so great that the amount they screw with each other is so small that you can't really make the argument that there's some kind of density problem, because there really isn't. And obviously there is inside the actual structures. The reason why galaxies look the way they do is because the matter is interfering with each other. Unfortunately, I may not be entirely... Okay, we already did that. Anyway, my gut says it's probably another wrong answer. Right. Who cares? I mean, it's not a gut R thing in the first place. And I don't know why you would think it's a wrong answer, again, when it does what the other theories haven't done for 2,000 years or 10,000 years or 50,000 years. Whatever the hell that was. In the sense that it's never provided a good model of magnetism. Now, in my opinion, perfectly explains magnetism and how it functions. And so it's outstanding compared to all the other theories. Now, if you want to point me to some place where they explain magnetism with a simpler or more complete model, like a more complete explanation, like it's perfect, or simpler, which they're not going to do, 2 plus 2 plus 2, go ahead. But again, so just to say your gut says it's like everything else. Well, it's so distinctively different. First, it unifies easily all the forces. And second, it does that thing with the magnetism thing, the outstanding thing, the thing that always seemed, every explanation seems so flawed. I mean, conventional physics just says virtual photon. They can't even come close to explaining it. Yeah, so screw you, anyway, and your gut. Better in many aspects than multiversing quantum wavics. I guess that's wavicles. More Newtonian and on the right track to somewhere. Well, anyway, but probably not true. Well, whatever. Who needs this shit? Your gut says it's probably not true. Fuck you. I'm one of those people who have a special resistance to being convinced of anything. Well, then you're stupid. As soon as I heard the theory of evolution, I said, oh shit, so obvious. Anyway, one of my defects. I would probably doubt the truth screaming straight into my face, whatever. Well then, fuck, what do I need this interaction for? How is this helpful in any way? Oh yeah, that's right, it's not. On the other hand, it helps me steer clear of wrong answers. Well, yeah, steer clear of any answer. Clearly, some answers smell a lot worse than others, though. Yes, that's my whole point. And you're just basically throwing mine in the same can and say it smells the same to your fucking gut. Well, fuck your gut. Finding the least wrong answers might just be the best we can do. Well, obviously, that's the best we can do. And we're not doing it, is my argument. Clearly, when we just let people make up shit and say, okay, we're going to consider the stuff you just, the cartoons, you come into court and you say, I think the Invisible Man did it, because I really don't want to do any investigation, I don't want to do any work, I don't want to have to tie all these facts together in some kind of coherent argument. I'll just say Invisible Man, right? Let's just get this over with. Fuck it. I mean, it's lazy and, just obviously you didn't even try to get the right answer. You seem to be more optimistic than me about this. It has nothing to do with optimism. It has to do with there's no other choice. I mean, there's only two things to do: sit here and eat their shit, or make a better meal. So, I mean, I have the choice not to eat the shit, so I'm not going to eat the shit, and I have the ability to make the better meal, so I'm going to do that. The ingredients are right here. We can mix it into something, or we can just sit around going, I don't know, I'm not going to bother thinking about it. I would say there's some questions not worth bothering with. Okay, how old is the universe? Where was all this crap about the long distant future or the long dead past. Forget about wasting your time trying to figure out how many warts Aristotle had on his forehead. Fuck that. Find something better to investigate. So anyway, sorry. This, yeah, sorry, but yes, sort of a waste of time. All right. So I guess I'll leave it there. I mean, there's lots of other stuff to do, but I'm obviously a bit stressed, and yeah, I want to get that animation thing right, and and so I have work to do, and so till the next time, and such, and so forth and whatnot. Yeah. Sorry, that's all there is for today. So far today. Maybe later.